Let us understand what are glands. A gland is an organ or a tissue mass in the body of an animal which synthesizes a substance or a chemical for release of hormones into the main bloodstream. There are two types of glands, endocrine glands and exocrine glands. Endocrine glands are ductless glands. They secrete their products directly into the main bloodstream. The main endocrine glands include pituitary, pancreas, ovaries, testes, thyroid and adrenal glands. Whereas exocrine glands have ducts leading into the lumen of other organs and they secrete their products through duct to the target organs. Thyroid is also a gland and it has its hormones. The thyroid glands are basically a hollow ball-like structure made up of a single layer of epithelial cells enclosing fluid-filled space. They are extremely important and have distinct functions as they act on almost all the cells of the body. Thyroid hormones are synthesized from amino acid tyrosine and they require iodination of these molecules for their synthesis. We will now look into the evolutionary changes in the development of thyroid glands. The evolutionary changes in the development of thyroid glands of different species over the years have matured it to its present state. Among cyclostomes and teleost fish, the thyroid gland is not well organized and is seen as scattered follicles, while in cartilaginous fish, it appears as unified glands. Amphibians possess double thyroid glands, which are round in shape and are firmly attached to the windpipe. In reptiles, such as snakes and turtles, single discoidal structure of thyroid gland is found. It is located in the front of the heart at branches of systemic aorta, whereas in lizards, thyroid gland is found in strip-like formation across the trachea. Birds have two isolated round lobes lying on either side of trachea at the level of their collarbones, whereas mammals have two lobes of thyroid gland lying on the ventral side of trachea and connected with isthmus. The mammalian thyroid gland develops through various stages. Initially, the solid primordium is penetrated by surrounding mesenchymal tissues and forms basic stroma and vascular supply. These primordial cells get separated into cords of cells and later these cords are separated into smaller cellular groups. The cells become visibly polarized and the nuclei of the cell moves towards the basal position of the cell. At this stage, intracellular droplets are found within the cells, which contained colloid-like material. Finally, extracellular colloid and follicles are formed. Follicles or follicular cells are lined by epithelial cells and the lumen is filled with coagulable fluid called colloid. These cells are capable of variation in shape within the same species and within the gland. Follicular cells synthesize thyroglobulin protein. The histology of thyroid gland is shown in the figure. The biosynthesis of thyroid hormone. Biosynthesis process is comprised of three phases. The first one is accumulation or trapping of iodide from circulation, iodination of tyrosine molecule and proteolysis of thyroglobulin. Let us understand the three processes in detail. The accumulation or trapping of iodide from circulation process requires iodine to appear in blood as inorganic iodide. The concentration of iodide in blood is very low, but the follicle cells have great affinity for inorganic iodide. In the second phase of iodination of tyrosine molecule, Inorganic iodide gets accumulated in follicle cells and then oxidized in presence of peroxidase enzyme into elemental iodine or hypoiodide. Thus, amino acid tyrosine first gets iodinated to form monoiodotyrosine, also known as MIT, which then gets one more iodine and forms diiodotyrosine or DIT. When mono and diiodotyrosines conjugate, it forms triiodotyrosine, also known as T3, and when two diiodotyrosines conjugate, it results in the formation of tetraiodotyrosine or thyroxine, which can be called T4 as is shown in the figure. Let us understand the biosynthesis process of thyroid hormone. It is a stepwise procedure that can be understood with reference to the numbers indicated alongside. Point 1 indicates the active uptake of iodine in replacement of sodium ion. Point 2 specifies that iodine may be discharged from the follicular cell by inclusion of competing ions such as perchlorate, bromide or chlorate. Point 3 shows that the thyroid stimulating hormone stimulates iodine uptake, an important point for hormone synthesis. Point 4 emphasizes that in presence of thyroid peroxidase, iodine gets oxidized by hydrogen peroxide to form active iodine. Point 5 illustrates how iodine gets actively transported to the surface of the follicular cell. Point 6 shows active iodine helps thyroglobulin molecules to form mono and diiodotyrosines, that is MIT and DIT. The 7th point displays thyroglobulin uptake that takes place into the follicular cell lumen, and finally, about 1% of stored colloid is removed every day. Proteolysis of thyroglobulin. Thyroglobulin directly cannot enter the blood because of its huge molecular size. The protease enzyme causes the proteolysis of thyroglobulin, and thus all the iodinated amino acids get released. Usually, MIT and DIT gets destroyed within the cells. Then the liberated iodine returns to the pool of iodine in cell, and that is being used in thyroidal iodine cycle. Understanding the thyroid hormones, their secretion and transportation to the target organs. The units of iodothyroglobulin, that is MIT, DIT, T3 or T4 from follicular lumen are taken up by follicle cells through phagocytic or endocytic mechanisms. Thus, colloid droplet is formed in the cytoplasm of the cells and fuses with lysosome and forms phagolysosomes. During this, hydrolysis of iodothyroglobulin occurs and T3 and T4 are released and get diffused into the capillaries surrounding the follicles as is shown in the figure. It is after this that MIT and DIT enter into the follicle lumen by the process of exocytosis, where the concentration is very low. And at that point, the amount of T3 present is almost 100 times lesser than that of T4. Even then, T3 is able to leave blood more easily and penetrates peripheral tissues because T3 has more affinity towards intracellular receptors as compared to T4. Thus, T3 has greater biological activity than T4. In presence of TSH, colloid droplets comprising of thyroid hormone within thyroglobulin are taken back into the follicular cells by pinocytosis process. Colloid droplets get fused with lysosomes that causes hydrolysis of thyroglobulin to release T3 and T4. About 10% of T4 undergoes monoiodination to T3 before it is secreted. Generally, 100 microgram of T4 and 10 microgram of T3 is released each day. Metabolism of thyroid hormone. No hormone that is produced in the body persists. Half-life period of hormones are different depending upon functions and nature of hormone. The thyroid hormone is chiefly metabolized in the liver and kidneys. The thyroid hormone undergoes three main processes: deamination, decarboxylation and deiodination, due to which metabolites are formed and then excreted by urine and fecal matter. The physiological effects of T3 and T4 can be seen in the fact that thyroid hormones are necessary for normal growth in children and young animals. They are considered as tissue growth factors and stimulate protein synthesis and degradation processes. Normal thyroid hormone levels are required for fetal and neonatal brain. Thyroid hormones also have remarkable effects on heart functions. They are necessary for normal hypoxic and hypercapnic drive to the respiratory centers. Thyroid hormones increase erythropoiesis due to increased oxygen consumption by tissues, leading to increased erythropoietin production. Thyroid hormones generally increase the metabolism and clearance of various hormones and pharmacologic agents. Thyroid hormones have a high stimulatory effect on bone metabolism, that is, increasing both bone formation and bone resorption. It affects almost all tissues and stimulates calorigenesis and thermogenesis. It yields increased milk production in lactation and is necessary for normal menstrual cycles and fertility. It affects carbohydrate metabolism in that it decreases glycogenesis and increases glycogenolysis. It also affects lipid metabolism in deficient state of thyroid hormones. Serum cholesterol level rises, and with excess hormones serum cholesterol levels decline. Disorders of thyroid glands. Basically, thyroid disorders are of two types: hyperthyroidism and hypothyroidism. Hyperthyroidism refers to the overproduction and hyperactivity of thyroid hormones and the accelerated metabolism in the peripheral tissues. The term hyperthyroidism and thyrotoxicosis are used interchangeably, irrespective of whether the disorder is caused by endogenous overproduction or excessive ingestion of thyroid hormones. Overproduction of thyroid hormones over a short or long period of time leads to many diseases or pathological conditions, including Graves' disease, non-cancerous growths of thyroid glands, tumors of testes or ovaries, inflammation of thyroid gland due to viral infections, ingestion of excessive amounts of thyroid hormone or iodine. The symptoms are hyperactive thyroid gland, restless, irritable, hyperactive, suffer from insomnia, anxiety, high heart rate, rapid weight loss, diarrhea, bulging of eyes and vision disturbances. Hypothyroidism refers to the condition where thyroid gland fails to produce enough amounts of thyroid hormones. The most common cause of hypothyroidism is Hashimoto's disease, where immune system attacks the glands. Risk factors include age over 50 years of age, which is very common in females, in case of thyroid surgery or exposure of the neck region to X-ray or other kind of radiation. Its symptoms include fatigue, weight gain, constipation, fuzzy thinking, low blood pressure, fluid detention, depression, body pain, slow reflexes, abnormal menstrual periods. Goiter is also caused due to thyroid imbalance, and its symptoms are enlarged thyroid, including a swollen, tender or tight feeling in the neck or throat, hoarseness or coughing, and difficulty in swallowing or breathing. Thyroid cancer in its early stages is asymptomatic. There may be a lump in the neck, change of voice, and difficulty in breathing or swallowing. Whereas thyroiditis can be characterized by pain and tenderness in the thyroid area, neck and throat, difficulty in sleeping. It can also trigger hyper or hypothyroidism. The signs and symptoms associated with both hypo and hyperthyroidism cannot be easily diagnosed as they are non-specific, and therefore laboratory tests play an important role in determining the stages and monitoring the therapeutic aspects. Measurement of thyroid stimulating hormone, total, and T3 and T4 and concentration of thyroglobulin protein becomes very essential for determination of disease state. To conclude, thyroid hormones regulate growth and metabolism, and therefore the normal levels of thyroid hormones becomes necessity for maintaining overall health. Thyroid tests are required for diagnosis and monitoring of hypothyroidism and hyperthyroidism. Accurate diagnosis and appropriate treatment of thyroid disorders thus depends upon the type of thyroid tests and thereafter the interpretation of the results. We started this topic by the definition of glands and the types of glands, that is, endocrine and exocrine glands. Development features of thyroid glands from fish to mammals we have seen, with major emphasis on mammalian thyroid gland development. Biosynthesis of thyroid hormone includes 3 steps, that is, iodine trapping, iodination of tyrosine molecules, and proteolysis of thyroglobulin protein. Then, we have learnt the basics of secretion, transportation, and metabolism of thyroid hormones through the graphical representation. As thyroid hormones are mainly involved in growth and development process, we have also studied the physiological effects of T3 and T4. Lastly, from the clinical point of view, we understood the role of thyroid hormones and what would happen to the normal homeostasis in lieu or in excess of thyroid hormones, and the symptoms of hyperthyroidism and hypothyroidism.